Okay. Thank you very much for the introduction, and thanks very much for the organizers of this wonderful workshop for inviting me. It is a great honor to present in front of this community. I'm very much a newcomer in the dynamic systems community. I myself am a data scientist at Pacific Northwest National Laboratory with control engineering background. And this work has been done in collaboration with my wonderful colleagues at PNL, Aaron Tuor, Somya Vashist, Mia Skomsky, and Drgona Vrabje, which is an assembly of engineers from various backgrounds, deep learning, aerospace, mechanical engineering, control theory, whose main purpose at the lab is to build simulation models for complex engineering systems for the purposes of optimization and control. That's our main business of operation, and applications range from power systems modeling and control, energy systems of buildings, unmanned vehicles, and similar systems. So we are providing probably a little bit different perspective on dynamic systems. We first build those systems and then we try to understand them, or like disassemble them into different parts and try to understand those constituting parts. In the recent times, like there is a crucial need for speeding up our simulations, especially when we are dealing with heterogeneous simulations, multi-scale simulations, and dealing with different physical processes combined together in complex systems. So scalability is one of the issues. Another issue is the cost of obtaining those high-fidelity simulations that typically takes an army of PhDs and months of development time in languages like C++ and Modelica to build your simulation model. So recently, last decade, there has been emergence of machine learning methods for coming up with surrogate models for replacing these complex physics-based models with cheaper machine learning-based models. So integration of machine learning and physics-based models is an emerging field. People call it physics-informed machine learning, scientific machine learning, differential programming. All these kind of labels can be fit in our business, what we are doing at the lab. With applications in optimization, modeling, and control of the dynamic systems, that's like really ubiquitous to all kinds of domains. But there are challenges when we are just doing data-driven modeling and plugging it in physics-based simulations that range from constraint satisfaction, some robustness guarantees, or stability guarantees. One of the most popular approaches, not the only one, of course, are neural networks. Just to take neural network and replace your physics-based component, and you have the solution, right? But not as easy. And one of the problems is let's certify those behaviors. Like, let's say we want to have stable dynamical system when we plug it in our computation. How do we come up with guarantees for neural networks? There are, I would say, three dominant approaches for certifying stability of neural networks that range from spectral approaches, when you do like eigenvalue decomposition of some matrices that can be your weight matrices, or it can be Jacobians, data covariance matrices of neural networks. Or you construct or verify your neural network that satisfies certain contraction constraints or Lipschitz bounds, or you design some energy-based functions like Lyapunov or Hamiltonians to either provide the dissipativeness or energy conservation properties of your neural net. So these are like three different angles of attack of this problem. And we took inspiration from all of these, and we want to study like one of the simplest dynamical system in terms of formalism. Like you have this discrete time and nonlinear dynamics that is defined by the mapping f theta, where the f theta is given by deep neural network. In this case, it's fully connected neural net. It's nothing else, just affine transformation followed by pointwise nonlinearity sigma, and that's it. Neural networks, being universal functional approximators, in theory, they can represent arbitrary vector fields, and here are just 6 toy examples of those vector fields. Single point, multi-point attractors, line attractors, all of them can be represented by neural network in theory, but in practice, when we train those neural networks, very often we end up with only a small subset of those attractors, and we found that it's very hard to learn complex multi-point attractors or even chaotic dynamics with using just simple mean squared error objectives without doing heavy regularization architecture design. That's interesting, and we want to figure out why it is so. We want to understand how these neural networks behave in the dynamic system context. And first we need to understand, or at least intuitively know, what are the individual constituting components of neural networks doing in the dynamic systems, being weights, biases, activation functions. Then we want to maybe put those neural networks in more analytically friendly framework. We will provide some refactorization of neural nets into piecewise affine forms, on the top of which we can do some dissipativity system analysis. Okay, so we have weights of neural networks. If you drop your biases and activation functions, you have simple linear dynamic systems, everything is known. That's super easy. So what are the weights actually doing in your neural networks? They define whether your dynamics will be stable or not. And they are also providing the basis of your eigenvectors, essentially. So they provide the potential for shaping your vector field. And that's essentially it. The complexity emerges from adding those activation functions, where you essentially cut your state space into different regions. That's what they are doing here. They are partitioning your state space into different regions where you have different local dynamics. And depending on the type of activation functions, you can have piecewise state space, where you have piecewise affine mapping, or you can have like smooth nonlinear transitions when you continuously shift from one local dynamics to another local dynamics. In terms of the effect on the eigenvalues, they are not, most of the activation functions, they are not doing much. They are just dumping your dynamics. For instance, activations like reloose or hyperbolic tangents that are very commonly used. They are Lipschitz continuous with a constant 1. That means that they will be either damping or just conserving your energy in the system. And this is just visualization of a range of different activation functions you may use. Most of them are really like stable, where these blue areas are the areas of your Lipschitz continuity with 1 contractive activations. Some of them can generate some energy system and destabilize.
You say they're contracted because of the boundedness between 1. This is for discrete time.
Yes, discrete time systems.
And without coefficients in front of them that you would learn.
Correct. Yeah, this is the very simple case. You have just discrete time autonomous dynamic system given by this deep neural network map. You can do various kinds of tricks. So you can have different architectures, residual networks, neural ODs, and like things are a little bit different there, but I'm talking about just direct maps. Great. Okay, what about biases? Like, you can think of the biases as just coordinate shifts. That's what they are doing, really. They are pushing the hyperplanes that are generated by activation functions not to go through your origin, but to have the shift outside of the origin. And they also determine your fixed point attractors if you are having stable matrices and stable activation functions. If you would drop all the biases and you will have only stable matrices in your neural network, you will always converge to the fixed point at the origin. While when you add those biases, like it will be doing coordinate shift and you will be converging somewhere in the state space. So there is some relationship in the center of the region of attraction with biases that we will explore later on. What you could do next, you can do deeper neural networks. So what is the effect of the depth on the dynamics? Let's look at the eigenvalue distribution of your layers, where in this figure, we have these distributions that give the density of the eigenvalues, and the x-axis represents the magnitude of the eigenvalue. Blue color is neural network with 1 layer. The orange one is 4 layer, and the green one is 8 layer. What we see on this left figure, that when we have stable weights, then the eigenvalues of the overall network by composition is shifted towards like more contractive map overall. And on the right-hand side, you are being pushed away to basically increase your eigenvalues. So this indicates this well-known vanishing and exploding gradient problem. So recently in neural network community, there has been like some agreement that when you are training very deep neural network or recurrent neural network, very often you want to have your weights initialized with eigenvalues closer to 1. That is this case, that those distributions are not like exploding too much. But deeper you go, like you are creating what they call these heavy-tailed distributions. Like you are pushing away those eigenvalues that dissipate, and you are pushing away those eigenvalues that are exploding. So that's the effect of the activations. That's a lot of degrees of freedom. These neural networks are not very friendly for analysis because exactly of this. Like you can tweak a lot of pieces. How can we understand them a little bit better by providing some refactorization that is more amenable to dynamic system analysis? And that's what we are doing here. We are engineers. We assemble systems that we disassemble them and reassemble them in different form. And in this case, we just provide equivalent piecewise affine reformulation of deep neural network, where your deep neural net is equivalent with this local linear transformation plus this aggregate bias term that is driven by your state. So it's a state-dependent affine transformation. So it's intuitive, like when you have like one initial condition, like in each region of each point in your state space, you have different affine transform. How do we obtain that? We observe the following, like it is just the composition of the affine transform with pointwise nonlinearity, where we can represent the pointwise nonlinearity as a state-dependent diagonal matrix, where on the diagonals, you have the activation patterns, the firing patterns of your activation functions. We tweak a little bit by using identity operation of addition and multiplication. It's just technicality, but it allows us to represent this local linear operator as a product of your weight matrices and these activation patterns, which are just diagonal scaling matrices, so they don't affect your eigenvectors, they just only affect their eigenvalues. And then this bias term is a recurrent product of contribution of your bias terms as they propagate through the layers of activations and biases. All right, now we have something a little bit more friendly. It looks like switch dynamic system or parameter varying systems that are very well studied in control theory. And there are a lot of statements we could say about them. I just go from like more intuitive approach. How can this be useful to have just one local operator of dynamic system? You could use it for visualizing your state space partitioning when you, let's say, evaluate the operator norms of these local linear maps, and this will allow you to plot the partitions of the state space that have different dynamical properties, or it allows you to compute the eigenvalues of the local operators evaluated on the sampled state space. So for different attractors, we have different eigenvalue distributions. And in the first row, like very simple attractors, fixed point or simple limit cycle, that indicates all the eigenvalues globally lie within the unit circle, stable dynamics, while for more complex attractors like quasi-periodic cycles or multi-point attractors, of course, you need to have unstable eigenvalues in your state space. But very often we see like this is the case in neural networks, and we want to figure it out why. So can we formalize it a little bit? So we use the dissipativity analysis to come to 8, and we have the simple dissipativity condition for discrete time dynamic system. You have what is called non-negative storage function that represents some scalar valued energy function representing the energy stored in the dynamical system. It has trivial null space and is non-negative. And then you have this difference between the energy at the next time step from the energy of the previous time step needs to be upper bounded by what is called supply rate. There's this S of xt. Again, it's state scalar valued energy function that represents roughly the energy that is supplied to the system. Like simple physical interpretation, you have a two-tank system. When the tank has a liquid and you have like a fluid flowing in, that's your supply rate. And the dissipation is like how much fluid is going out. And basically you need to satisfy that the condition that energy stored in the system is less than energy provided into the system. Then you have dissipativity that holds. And it's essentially extension of the Lyapunov stability for open systems. Why we are talking about this? Because when we look closer at the piecewise affine reformulation of the neural network, we can tweak it a little bit, and from the conceptual perspective, we can look at it as a dissipative system where the local linear operator would be representing your storage function, and the bias term could represent the supply of the energy. Okay, and then I'm claiming that if you have contractive local linear operator in this local affine transformation, then this deep neural network is dissipative with respect to specific supply rate that is just the 2 norm of your aggregate bias vector. So you can think of it, okay, my activations and weight matrices all together, if they are contracting, then you have dissipative system because you are not storing energy despite of your bias terms that are like feeding the energy in the dynamical system. So that's the intuitive interpretation of this statement that is very simply proved through just basically leveraging the submultiplicativity and the subadditivity of these operator norms. So it's a rather simple storage function that's a just simple quadratic one that allows us to say something formally about it. What are the implications of this? Like we know now that globally we can have attractor, but we don't know anything about the shape, and we don't know where the steady state lies even if we have it. So there is also some condition that I don't want to go into too much details, but intuitively, basically, it says that for stable systems, if we have the dissipativeness on the local linear attractor, the steady state, the region of attraction shrinks with the smaller bias. So if our bias dissipates to 0, the region of attraction shrinks to 0. That's like intuitively what we have been showing. When you have 0 bias, you are converging to 0 to the origin as your steady state. So larger the bias, further away are you going from the origin, and larger the contraction, closer you are going to the origin. So this is kind of the balance between these two. So if you are close to the to spectral radius equal to 1, and your bias is rather large, like you can lay your steady state can be anywhere almost in the state space. So these are kind of the intuitive principles which we can now apply in designing these neural networks with desired steady state properties if we know something about the system. Another property which we can leverage is submultiplicativity of the operator norms. So now when we have this local linear operator given by the weight matrices and activation pattern matrices, we can just say, okay, let's design weights to be stable, activations to be Lipschitz continuous. Then we can guarantee the contractivity of the local linear operator. And for that, we have been developing some straightforward linear algebra factorizations to replace standard weights in deep neural networks. So this is our main business. We code up the dynamical systems or physics-informed machine learning models, and then we combine them in a modular form. In this case, I'm just showing two types of factorization you may want to use if you want to constrain your eigenvalues or singular values of the weights in the neural network. One straightforward way is to, instead of training one matrix, you are going to learn parameters of three matrices, left and right orthogonal matrix, and the diagonal scaling matrix that can be clamped through this straightforward expression to represent your singular values. And how do you satisfy the orthogonality? You can either use some soft constraints penalties or some householder reflections. So there are more details in those references I provide here that list roughly up to 20 different linear algebra-based factorizations for deep neural networks. Why it is important for us? Because many real-world dynamic systems have properties like dissipativity, let's say building thermodynamics. It's a heat equation, PDE, that is discretized in a state space, is reduced to the system of ordinary and differential equations, and we know it's dissipative because it always wants to get to the thermal equilibria with the environment. And if we are going to learn the surrogate model for a complex dynamic system with hundreds of states, we don't want to just use black box neural networks. We want to leverage these type of properties that we know, and these are the techniques we can use in practice to implement them. So that's from the practical perspective. From more a little bit of theory / empirical exploration, we have been trying similar concept in stochastic dynamic systems in the context of deep Markov models, where the evolution of your state is driven by the Gaussian distribution, where the mean and the variance now are generated by two neural networks. There are two independent neural networks. And again, the intuition holds similarly, like when you have contractive mean and bounded variance, your distribution will converge somewhere. It will not blow away. But when you violate this contractivity on your mean, like your trajectories will be all over the state space and like your distribution will be expanding. So if you are interested in stochastic systems and the application of this contraction theory and dissipativity, like you can check the paper that is listed over here or shoot me an email. And here is essentially where I want to finish up my talk and concluding or wrapping up the connection between deep neural networks, how individual components of deep neural networks affect the dynamics when we use them in the context of discrete time dynamic system, how we can reformulate deep neural networks in these local affine transformations that are more suitable for dynamic systems analysis, and then how can we go one step back and look at the individual components of the neural network and see how they satisfy certain dynamic system properties like dissipativity for us to design stable dynamic systems for system identification. For practitioners, we encourage to check our open source GitHub repositories. It's just drop-in replacement. If you are using PyTorch, you don't need to use the standard ways. You just use this object, and it will work off the shelf. You can contact me via email or add me on LinkedIn. And I want to conclude this talk by thanking our sponsor, which is Department of Energy Office of Science, for supporting our work. Thank you very much.